Hi guys, so today we're gonna talk about explaining the analogy between heat and mass transfer, and we can explain the Lewis relation as well. So Lewis number is essentially comparing mass transfer to heat transfer. Um, so first we're gonna look at heat and mass transfer individually. So for mass transfer, we're gonna use the Sherwood number. So it's a dimensionless number to determine how fast a mass transfer process is. And Sherwood number is going to be equal to Kc times L over dAd. So Kc is heat, Kc is mass transfer coefficient. And then L is length. Then dAb is diffusion coefficient. And then now we're gonna move on to, and also we can also expand um ma- Sherwood number in terms of concentration. So it's gonna be concentration times Reynolds number to the power of m times Schmidt number to the power of 1/3. And for heat transfer, it's gonna be we can use Nusselt number, and that's gonna be K to H times L over K. So H is heat transfer coefficient, L is length, and then K is thermal conductivity. And when we write in terms of concentration, we can have concentration times Reynolds number to the power of m times Brandel's number to the power of 1/3. And so what we're gonna do next is we're gonna divide them both. So we're gonna do mass transfer divided by heat transfer, because essentially what we stated before is that Lewis number is the ratio of mass transfer to heat transfer. So we're gonna have Kc, and we can cancel out L as well. So Kc over dAb times K over H. And we can also write that in terms of the concentration. So we're gonna have concentration Reynolds number can cancel out. So it's gonna be the Schmidt number divided by Prandtl's number to the power of 1/3. And so we know that Schmidt number divided by Prandtl's number is Lewis number, which is written under the expression A times rho times heat capacity times, and so K is just, thermal conductivity, and then mass transfer coefficient. And so we can replace that in there. So we would have Kc over dAb times K times A over H is equal to this to the power of 1/3. And so we can, in terms of Lewis number, so we know that K Lewis number is K over rho Cp Kc. And so that's L Lewis number, and then we can times it by rho C So essentially, we can let's imagine this situation where we have a surface of water and this is the surface, and then air is flowing this way, and it's gonna supply energy to water. So that's why the temperature of air is gonna be lower. And I was sorry, I made a mistake earlier. I meant to say air is supplying water with energy instead of so the temperature air is gonna be lower. So we're gonna derive an equation, okay? So heat transfer equation, H times area surface area times the temperature of air of water minus temperature of air. And then so like we did earlier, the amount of energy released by air is equal to latent heat of water or the heat of vaporization of water. And this is how the equation's written. It's going to be lambda times Kc times surface area um times concentration of the interface of water. Concentration of water at the interface divided by concentration of water at infinity. So this is the interface, and then this is the infinity. And so this equation is saying lambda is latent heat of vaporization, by the way. And it's saying how much heat needs to vaporize water. And this is a energy balance equation. And so we can as we did earlier right earlier over here, H is equal to Kc times rho Cp. So we're gonna replace that term over here. Rho Cp times Kc times A T water minus T air is equal to rho Kca lambda Kca concentration of water at interface minus concentration of water at infinity. And so now we can cancel out Kc and A, and we have rho Cp T water minus T air is equal to lambda times concentration of water at interface minus concentration of water at infinity. And so now let's leave that over here for a little bit, and then we can move on to adiabatic. So for adiabatic, let's imagine the scenario where there's a tube with water. Air's coming, air's coming in, and then there's initial temperature and then the final temperature out. And so for the adiabatic equation, since there's no heat in or out, air water is required to draw energy from the air, heat from the air to vaporize. So essentially T1 is gonna have a higher temperature than T2. So, and the concentration of water at the outlet is going to be higher than at the inlet. So we're gonna write the equation like earlier. So we have HA times temperature at output, input minus temperature at the output is equal to lambda Kca times concentration of water at 2 minus concentration of water at 1. So 2 at 1. And so we do the same protocol, rho Cp Kc to A T1 minus T2 is rho Kca Cwa minus Cw1. Cancel out Kc and A. We essentially have the same expression as above. And so it's just basically saying that for both wet bulb temperature and adiabatic saturation temperature are similar process where you draw heat from air to vaporize water that diffuses into the air, and it connects both mass transfer and heat transfer process. And s- and therefore, from these two equations, we can derive an equation for a concentration at the outlet. So C2 would be equal to rho Cp times T1 minus T2 over the over lambda plus C1. So that's our final equation. Thank you for listening.